wave. So wave is a disturbance it is a disturbance from equilibrium position So that disturbance travels from one place to the other place, from one place to other place. But here the important thing is, while the wave is propagating, the particles do not travel. The particles do not travel. So instead of traveling, instead of displacing they from one position to another position, generally the particles will oscillate. Particles will oscillate. Particles will oscillate. So generally in the wave propagation, so energy and as well as momentum, energy and momentum will be transferred. So these are the key points for a wave discussion. So here the particles do not travel, but the energy and as well as momentum, will be carried forward. So now we will see the classification of the waves on different categories. So for example, first I am taking, so this is a wave and the waves are divided into two categories. So waves are divided into two categories. So first one is mechanical wave. First one is mechanical wave and the second one is non-mechanical wave. So on the basis of availability of medium, we have been dividing it into two waves. One is mechanical waves and the other is non-mechanical waves. So generally this mechanical wave obviously requires medium. Definitely it requires medium. So whereas the non-mechanical wave, it do not require medium. It do not require medium. For example, if you take example, we are taking sound waves. We will take sound waves and waves on string. Waves on string and waves in air column. Waves in air column we will take. So when we think of the example of non-mechanical waves, so we will take light waves or EM waves we used to take. Light waves or EM waves. So obviously they don't require any kind of medium. And also we have further classification of the waves. So again, on the basis of displacement of particle, we are classifying the waves into two kinds. One is transverse wave and the other one is longitudinal wave. One is transverse wave and the another is longitudinal wave. So in the case of transverse wave, the particles will vibrate. The particles will vibrate in the perpendicular direction. To propagation of wave. So when we think of longitudinal wave, the particles they used to vibrate along the same direction of the wave. or in the direction of wave. So we are taking one example. For example, if we take, we will say waves on a string, and here we will say sound waves, in a wave. And when we think of rigidity, when we think of the transverse wave, so the medium, obviously it requires a medium. So that medium should have, so it should have rigidity. The medium should have rigidity. And it is possible in solids and as well as liquids and as well as gas. So these longitudinal waves are also possible in solids and as well as liquids and as well as gases. So generally in the waves we will represent a y as a function of x comma t. Here y has many meanings. Here y has many meanings. Y may be displacement. We will call it as displacement, or we will call it as pressure, or we used to call it as density, and the electric and magnetic fields. Electric and magnetic fields. So we can denote we can denote it in any manner. So the basic condition for the wave, that is, so the dou square y by dou t square equivalent to some k is a constant, some constant into dou square y by dou x square. So this is the required condition when y is given as function of x comma t. Suppose if it is given as y is equivalent to function of x comma t, then to satisfy the y as a wave, so definitely this condition to be followed. So it needs to be obeyed. It needs to be obeyed to prove y as a wave. So that is mandatory condition. So here is a constant we are taking and which is not equivalent to 0. And the most important point is y should be well defined. Y should be well defined for any values of, y should be very defined for any values of x and t. Y should be well defined for any values of x and t. Y should be defined for any values of x and t means, suppose if you substitute any value of x, so right from 0 to infinity you can substitute. So the y should be well defined. Y need to have some values. So this is very important point. On the basis of this point only, we will simply check out whether the given equation is a wave or not. So we will do that one. For example, if I am taking y equivalent to a sine omega t minus kx, y equivalent to a sine omega t minus kx is the representation of a wave. So first I will do dou y by omega t. So therefore I will get omega a into cos of omega t minus kx. So if we take dou square y by dou t square, again differentiation we are taking. So then I will get omega square a into, for cos we are having sine omega t minus k. Simply on the right side I am doing dou y by dou x. With respect to the x we are taking. So we get minus omega a into cos minus omega into cos of omega t minus kx here. So when we think of dou square y by dou x square again, sorry, this will be minus ka into cos omega t minus k. For for sine we are having cos, but again for minus kx we need to do, so that's why we are taking a negative sign. So if we take the differentiation with respect to the x, so this minus ka into, for cos automatically we have minus sine into omega t minus kx. But for minus kx, again we will get minus k. So that equivalent to finally minus k square into a into sine omega t minus k. So by comparing those two, we will get dou square by dou t square is equivalent to omega square by k square into dou square y by dou x square. So this is a very popular equation. This is a very popular equation. So we will write dou square y by dou t square equal to omega square by k square into dou square y by dou x square. So after that, or else we will write it as dou square y by dou t square equivalent to omega by k means. So simply we will write it as wave velocity. Wave velocity whole square into dou square y by dou x. So this is another relation, another important relation to understand the wave nature. So dou square y by dou t square equal to wave velocity whole square into dou square y by dou x. And the next important point is, when y is a function of x comma t, let us say, generally it is in the form of ax plus or minus bt. Generally it is in the form of ax plus or minus bt. So here we will say that here a comma b are constants. A comma b are constants. And we will understand that just by differentiating this term, easily we will know the direction and as well as magnitude of velocity. So we will discuss it later. So first we need to understand the exact meaning of a wave. So when it is when the given function is acts as a wave and when it not acts as a wave. So here I will explain with few examples. So these are very famous. Suppose y is given as log of x plus 2t. X plus 2t. So we need to check out whether this is a given the function is a wave or not. Okay. So this is not a wave. This is not a wave. So simply because for any value of x and t, so for any value of x and t, we can't define, we are unable to define the log of x plus 2t. So we are unable to define for all values. So that is not a wave. Second one I am taking, we are taking one example, y equivalent to some, we are having a fraction like this, 1 by 2x plus 3t. So whether we need to check y is well defined or not. Suppose if we take 2x plus 3t as 0, so then y is not defined or it can be undefined. So therefore it is not a wave. It is not a wave. For example, I am taking the next session like y is equivalent to e power minus x minus vt whole square. Y equivalent to e power minus x minus vt whole square. So it is a wave. It is a wave. So because for any value of x and t, suppose if we take x is equal to 0 and t equivalent to 0, So nothing but e power minus 0 we are having, y is equivalent to, so y equivalent to 1. So that means it can be well defined. It can be well defined for any value of x and t you can take. So when you take x is equivalent to infinity or t equivalent to infinity also, we can define it. So y equivalent to e power minus infinity square or 1 by e power infinity whole square. So that equivalent to 1 by infinity means 0. So it is obviously well defined. So it is a wave, but this wave is not harmonic. So we do not have sinusoidal terms, but not harmonic here. And we will see, so we are saying y is equivalent to x plus 2t whole square. Y equivalent to x plus 2t whole square. Suppose if x is equal to 0, t equal to 0, we can define y. But if x plus 2t equivalent to infinity, if x plus 2t equivalent to infinity, so y is undefined. Undefined. So therefore, this is not a wave. This is not a wave. So that means this is the very important condition you need to understand. Y should be well defined. Y should be well defined for any values of x and t. It can be definable for 0 or it can be definable for infinity also. So now we are going to see a beautiful one. For example, y equivalent to 2 by 3x plus 2t whole square plus 4. Y equivalent to 2 by 3x plus 2t whole square plus 4. So we need to check whether this is the wave or not. So we can check values. Let us say x is equal to 0 and t equivalent to 0. So obviously y is having some value. Y equivalent to 2 by 4, we will get that equivalent to 1 by 2. And if x is equivalent to infinity and t is equivalent to infinity also, so automatically something by infinity means y is going to be 0. So definitely, so this is a well defined. Only we will check these two values. So automatically we will call it as a wave if they are well defined. So definitely this is a wave. This is a wave, but obviously not a harmonic one. But not harmonic one. But not harmonic one. So now, how we will understand the velocity of the wave? How we will understand the velocity of the wave? So we are taking a simple logic. For example, if y is given as a function of ax plus bt. Suppose y is given like this. So simply we will understood that. So this function, that function should be a constant value because it is a well defined. For any value of x and t, it should be a constant value. So therefore, I am taking ax plus bt is equivalent to constant. So we will differentiate on both sides. So therefore, we will get a into dx by dt plus b equivalent to 0. So a into v plus b equivalent to 0. So v equivalent to minus b by a. So from this, we got two meanings. Negative means, so this is a wave. This is a wave traveling in negative x direction. This is a wave traveling in negative x direction. And if you are interested in the magnitude, so simply we will say that is b by a. So simply we will say this is b by a. Suppose if y is a function of ax minus bt, let us say. So for any value of for a given value of x and t, it is a constant. So by taking differentiation, we will get a into dx by dt minus b equivalent to 0. Automatically v equivalent to plus b by a. So therefore, its magnitude is v by a, and the wave is traveling this wave is traveling in positive x direction. Wave is traveling in positive x direction. So now we will check some another form of wave, that is wave pulse. For a while we will think of wave pulse. Suppose it is given y equivalent to 10 by 5 plus x minus 2t whole square. So what is our duty is we need to check whether this is a wave or not. And if this is a wave, we need to find out the velocity, amplitude and direction of propagation. So obviously this is a wave and we used to call it as wave pulse because for any value of x and t it can be definable. And we will take that x minus 2t as constant according to our previous discussion. We will differentiate on both sides. So we get dx by dt minus 2 is equivalent to 0 and v equivalent to plus 2 meter per second. So therefore, this wave pulse is propagating along the positive x-axis. So it is propagating along positive x-axis. And if we substitute x is equivalent to 0 and t equivalent to 0, so we will got the y as maximum that equivalent to 10 by 5 that equivalent to 2 meters. So when we say y maximum, the displacement maximum, automatically it is amplitude equivalent to 2 meters, we will say. Amplitude equivalent to 2 meters. So next, for example, if we take y equivalent to 1 by 1 plus x square at t equivalent to 0 seconds, and also y equivalent to 1 by 1 plus x minus 1 whole square at t equivalent to 2 seconds we are taking. So generally the wave pulse, maybe it is in the form of some b by q plus ax minus bt also. Generally that will be the so by comparing these two, a equivalent to 1 we will get, and bt is equivalent to 1. So actually the time value is given is here 2. So therefore b into 2 is equivalent to 1 or b is equivalent to 1 by 2. 1 by 2. So we have another nature for the wave. So we will define it as coefficient of t by, and that is coefficient of x. So simply by taking the differentiation like the previous one, we will get this kind of relation. So that is nothing but b by a. I'm taking here. So b by a means 1 by 2 by 1, that equal to 1 by 2. 1 by 2. So we got plus 1 by 2. So therefore the wave pulse traveling in positive x direction. The wave pulse is traveling in positive x direction. So in this way, we will understand a wave. And in the case of advanced exams, so we are having one more question also, that is, we need to check whether the given equation is symmetric or unsymmetric. So we will do here. For example, 4x plus 5t, y equivalent 0.8 by 4x plus 5t whole square plus 5. So here in this question, we need to check out the velocity and as well as propagating direction. And we need to check the value of, we need to check the nature, whether this is symmetric or what, not symmetric. Suppose first I am taking this 4x plus 5t as a constant as usual. So when we take the differentiation as 4 into dx by dt plus 5 equivalent to 0, velocity equivalent to minus 5 by 4, so that equivalent to minus 1.25 meter per second. So automatically the wave is propagating along negative x direction. Propagating along negative x direction. So we need to check whether this equation is symmetric or non-symmetric. So for this one we have a relation. If y as a function of x is equivalent to y as a function of minus x, so then the wave is said to be symmetric. The wave is said to be symmetric. So therefore, so this is a symmetric one. This is a symmetric. And we are taking harmonic wave equation. We are taking harmonic wave equation. So just now we have taken when y is a function of like this ax plus or minus bt. So then velocity of the wave is v by a. Just now we have taken a equivalent to v by a. Or else, suppose if the sinusoidal wave equation is given as y equivalent to a sine kx plus or minus omega t plus or minus phi. So then velocity of the wave is nothing but coefficient of time by coefficient of x. So that is the beautiful formula. Already we have taken coefficient of time by coefficient of x. Coefficient of time is nothing but omega, and this is k. This is very popular and very important. So v represents the velocity of the wave. That is very important. And next thing we need to think of phase. So when y equivalent to a into sine of omega t minus kx plus phi is a given situation, let us say. So in that equation, this whole term represents phase. This whole equation represents phase. Or we will call y equivalent to a sine. Instead of omega, we will take 2 pi by t into t minus 2 pi by lambda into x plus phi. Or we will take a sine into 2 pi by t means 2 pi frequency into t minus 2 pi into x by lambda plus phi. So these are the different forms. So actually, sometimes there is a need for initial phase. Initial phase. So initial phase means this is equivalent to the phase when x is equivalent to 0 and t equivalent to 0. So therefore, we know very well about the phase. So I am substituting there. So that is nothing but omega t minus kx plus phi. But the thing is, you need to substitute the value of x and as well as time. X and time. So we need to substitute both as 0. So automatically we are going to get the initial phase as phi. Initial phase as phi. And we have some applications of those one. For example, if it is given as y is equivalent to 2 sine pi by 2 into 2t minus 5x. So here the question is, find the particle speed, find the particle speed at the origin, find the particle speed at the origin at t equivalent to 0, comma 1, 0, comma 1 seconds. At the origin means automatically x is equivalent to 0. So this is the first question. And also the second question, at x is equivalent to 2 meters and when t equivalent to 6 seconds. So in that case, first we need to think of particle velocity. So here you need to be very careful regarding the particle velocity and as well as wave velocity. Both are different. So particle velocity is nothing but we will take dou y by dou t, dou y by dou t. So that equivalent to, we will get 2 into pi by 2 into, instead of sine we are having cos, 2 into pi by 2 into 2. So we have another 2. Because after differentiation we will get pi by 2 into 2 outside, 2 into pi by 2 into 2. And that is cos of pi by 2 into 2t minus 5x. Or simply we will write 2 pi into cos of pi t, cos of pi t minus pi by 2 into x. So now we are taking at x is equal to 0. First one we are taking at x is equivalent to 0. We are taking at x is equal to 0, Vp equal to 2 pi cos pi t. Suppose if t is equivalent to 0, we get Vp equivalent to 2 pi, and t is equivalent to 1, we will get 2 pi into cos 180 minus 2 pi. And when t equivalent to, and we are taking the next question when second one we are taking at x is equivalent to 2 and t is equivalent to 6. So simply we will substitute in Vp equal to 2 pi into cos of pi into t means 6 minus pi by 2 into x means that is 2. So 2 gets cancelled. 6 pi minus 5 pi means 5. So 2 pi into cos pi. Cos 180 is minus 1. So therefore minus 2 pi. So in this way we will estimate the particle velocity. And here the most important formula for the particle velocity. So here we will take so the relation between particle velocity and wave velocity. So that is particle velocity Vp equal to minus wave velocity into slope of displacement, slope of let us say slope of yx curve. So already we have proved in this in the earlier discussion. So just now here we are having dou y by dou t and as well as dou y by dou x. If we divide those two, we will get in the terms of minus omega by k. So that is nothing but the wave velocity. So this is very important. Or simply we will control it as Vp equal to minus velocity of the wave into dou y by dou y by dou x. So when we have the equations of y and x, so we will calculate the velocity of the particle like this. Or otherwise, we know that the particle will execute SHM while the wave is propagating. So we will use the SHM principles also. Sometimes when there is a need, we will use the SHM principles. Vb equivalent to omega into root over a square minus y square. So after that one, we will think of the acceleration of the particle. The acceleration of the particle. So when we think of the acceleration of the particle, just now we have studied as the particle executes SHM. So therefore SHM relations are valid here. So therefore I am taking AP equivalent to minus omega square, right? AP equivalent to minus omega square. So we need to understand this. So from this we will conclude that as the acceleration direction is towards negative displacement. So that means, for example, if this is the propagation of the wave and this is the particle displacement y, and we will see that acceleration of the particle is towards mean position. So therefore, the force is always towards mean position. So we will take one example of this. For example, we have a graph which represents the wave. And the wave is propagating, velocity of the wave is propagating 10 centimeters. And also in the question, the wavelength is given as 0.5 meters, 0.5 meters. And amplitude, this amplitude is given as 10 centimeters. So now the question is, find the velocity of the particle, which is at a distance of 5 centimeters, from mean position. So we need to understand this. Suppose 5 centimeters. 5 centimeters means we need to understand this. Velocity of the particle equivalent to omega into root over a square minus y square. So by substituting here the respective values, so we know velocity of the wave that equivalent to omega by k, omega by k. Already we know the value. By substituting here, we will get the root 3 by 50 centimeters. So when this is at 10 centimeters, first we need to locate the 10 centimeters. So because lambda is equivalent to 0.5 meters, so therefore from here to here is 25 centimeters. From here to here it is 25 centimeters. So in the 25 centimeters, so we need to discuss at a position 5 centimeters. So that means the particle may be located here. The particle may be located here. Suppose the particle may be located here. So in that case, we will observe if this is a yx graph. So then dou y by dou x is equivalent to positive. So then dou y by dou x is equivalent to positive. Already we have a relation Vp equivalent to minus velocity of the wave into dou y by dou x. So that means so the velocity of the particle is going to be negative. So velocity of the particle is going to be negative means it is in the downward direction. It is in the downward direction. So in this way, we need to analyze the exact position of the particle and the wave. Next, we have phase difference. Phase difference when the given equation is in the terms of time. So that is if the y equal to a sine into uh, kx minus omega t. So this is given as a y as a function of time. Y as a function of time we will say. So in that case, we will find out the phase difference as 2 pi by t into delta t. And when y is a given as a function of position, omega t minus k. So then the phase difference formula we will write it as 2 pi by t into delta x. 2 pi by t into delta x. So this is about the analysis of a wave and wave equation nature and particle velocity. So after this, we will slowly begin the discussion related to the wave speed in a string. Wave speed on a string. So that is transverse wave velocity. Transverse wave velocity. So that means we are going to speak about the strings. So whenever we used to think of a string, so which is rigidly between the two ends, and it has a tension P, and mu is the linear mass density. Mu is the linear mass density of wire. So that means mu equivalent to mass of the wire, by length of the wire. Mass of the wire by length of the wire. So we have many possibilities right from here. V equivalent to root over T by mu. So V equivalent to root over T by mu means, so we can substitute, so instead of T, we can apply the force. We can apply any logic of force, we will see. We will apply any logic of the force. And simply we will say V equivalent to root over T by mu means arrow, or we will take root over T by area of cross section means pi r square into 2. Pi r square into 2. And also we will consider when elasticity is taken into consideration. So we will write this T by A as force by A into rho. F by A is already known to us. So that is y alpha delta theta F equal to ya alpha delta theta. Already we have a formula in elasticity. From there we are writing F by A equal to y alpha delta theta by rho. This is very important one. So this is very important. And if you need the elongation, we have a formula delta L is equivalent to L alpha into delta theta. So delta L can be considered as elongation or no issues delta L. Delta L by L is equivalent to alpha into delta. So therefore, we have another form V equal to y by rho into delta L by L. Delta L by L. So in this way, we have some models of velocity as V is proportional to root of delta L. So all these are very famous discussions. V is proportional to root delta L. So actually, these are very important. These are very, very important. We need to understand. So this is V equal to root of T by mu. And every formula is famous here. So we need to memorize all. For example, if we have the string and that string is connected to load, let us say, load of mass M. And this mass having a density ds, suppose if it is immersed in a liquid of density dl. So generally, in the absence of the liquid, directly we will write the T, but after taking the buoyancy, so we will take the tension in this way. So we will write it as mg dash. After taking buoyancy into consideration, we have a logic mg into 1 minus dl by ds, or mg into 1 minus 1 by specific gravity. 1 minus, we will write it as specific gravity. So this is also one important model. Or else we are having an application. So this is a pulley. From the pulley we are hanging body. Simple case I am taking. So when the body is hanging, just we will write the tension as the mg. So now we will apply the formula V equivalent to root over T by mu. Root over T by mu. So here m is nothing but mass of hanging body. Mass of hanging body we used to take. For example, I am taking a string which is pulled over a pulley and suspended with a 10 kilogram load. Suspended or 10 kilogram load. And the linear density of the wire is given as 10 gram per meter. And the distance of the student table is nothing but 10 meters. Now the question is, find the velocity. What is the velocity of the string? What is the velocity of the string? And you need to find the time taken. You need to find time taken by the wave to travel along the length of table. Along the length of table. So first we will find out the velocity of the wave V equivalent to root over T by mu. So tension is nothing but hanging part load by mu. So that equivalent to root of mg means 10 into g, we are taking 10, and mu is 10 gram per meter. 10 into 10 power minus 3. So finally, we are going to have 100 meter per second. That is the velocity. So now the velocity is propagating So the wave is traveling this 10-meter distance. So with a velocity 100 meter per second, 100 meter per second. We know that the wave velocity is constant. So therefore we will write time equivalent to distance by speed. So that equivalent to 10 by 100, that equivalent to 0.1 meter per second. So 0.1 meter per second. So here, so we have few important things. So this is very, very famous. So when a wire of length L, when a wire of length L suspended from a support, then find the velocity of the wave at any instant or at any position, and velocity of the wave at any position x from bottom. Velocity of the wave at bottom position and velocity of the wave at top, and next one, acceleration of the wave, and the last one, time taken by the wave, to reach the top from bottom, So this is a very famous one and important one. For example, this is a support we are taking. This is a wire of length L. So at a distance x, we are observing a point P. So first we will understand the tension. Tension is nothing but weight of hanging part for hanging bodies. So the hanging part is x length and it have a density mu. So therefore mu x is the mass and g. Mu is the linear density per unit length. Per 1 meter length we have the mass as mu. So for x length we are having mu x as the mass. So therefore velocity of the wave v equivalent to root over t by mu we are taking. So t means mu x into g by mu. So v equivalent to root x g. This is a very famous problem. V equivalent to root over x. So after this, so this is the first one. Second one, we are taking velocity at the bottom. So from the bottom itself, the x is measured. So therefore x is equal to 0. Velocity will be 0. So then velocity at the top. So x is equivalent to L. So therefore we will take v equal to root over g. And fourth one, acceleration. As the velocity is a function of x, so generally we have a logic a equivalent to v into dv by dx. So in that case, we are taking velocity is root gx and dy by dx means 1 by 2 root gx. For 1 by x, we are having 2 root gx. And again for the that the xg, we need to take the differentiation. So finally, we will get acceleration equivalent to g by 2. And we need the time taken to reach the top. Suppose it starts with velocity 0 and the distance covered s equivalent to L we are taking. So after taking s is equal to ut plus half it square, we will get s is equivalent to half it square or t equivalent to root of 2s by a. So that equivalent to 2 into s means L and acceleration means c by 2. So therefore T equivalent we will get 2 into root of L by G. So T equivalent to root of L by G. So after that, so we will discuss about the energy of a wave and intensity. So we will think of energy of a wave. So simply we will remember the energy. Now simply we will remember the energy. So by taking SHM, energy or as well as power. So first we will study the basics. Later we used to think of a lot. Du by dx or that is equivalent to dk by dx. Change in potential energy with respect to x or change in kinetic energy with respect to x. So that equivalent to half mu into omega square a square into cos square of omega t minus kx here. So when we think of total energy d by dx, half of get added because energy is nothing but dy. This is dy dx of u plus k only. So finally we are having mu into omega square a square into cos square of omega t minus a. And now we are taking about the power p equivalent to d by dt, d by dt actually, or we will call it as d by dx into dx by dt. So that is nothing but v into d by dx. So therefore finally the power equivalent to we will say mu into omega square a square into v cos square of omega t minus k. This is very important. So this is called as instantaneous power. So because as the power is mentioned in terms of time, so we will call it this as instantaneous power. And now we will think of average power. Average power equivalent to half into mu v square mu v into omega square. Now we will remember this average power with a beautiful shortcut. Average power equivalent to just so this is average power means energy by time. So as we know, generally the particles are doing executing SHM. So therefore I am taking SHM energy half an omega square a square by t. Mass means area into length into density. Or we will take it as like this, half into m by l into l by t into omega square a square. Or half m by l we are taking as linear density and l by t is the wave velocity omega square a square. So in this way we will easily remember the next intensity. Intensity I is nothing but energy by surface area into time. Already energy by time means power by surface area. So therefore half mu into v into omega square a square by area. Actually S means area of observation. Half mu into mu means already we know about as arrow into v omega square. Not exactly a means here the area. Linear density means S rho into v omega square a square by s. So here s cancel. We get half rho into v into omega square. Our intensity, popularly known as this equation, I equivalent to 2 pi square f square a square 0. So this is the most famous representation for the intensity. This is very important. So where rho is the density, here rho is the density, and v is wave velocity, a is amplitude, and f is the frequency.